Leia here from leiafirsci.com, and in this Orgo Basics video, I'll show you how to draw the Lewis structure for organic molecules, and then a checklist to help you determine if you did it correctly without second-guessing yourself. I'll start off by saying that this method will be slightly different compared to what you learned in school, but as a tutor I've been teaching this for a decade and my students get this concept quickly, so it's definitely worth giving it a shot. The checklist is as follows: atoms, octet, electrons, and formal charge. If you can check off every item on the checklist, there is a very high chance that you got it correct, and if you made a mistake, the checklist will help you catch that. We'll use a simple example to learn the list and then tricky examples to prove that it works. Let's draw the structure for C2H6. We'll start with the atoms, specifically the least electronegative atoms other than hydrogen. The reason I say other than hydrogen, the hydrogen atom can only have one bond. So if we put a hydrogen atom in the center, you make a bond to one atom, you're done. You can't add anything else. But other atoms such as carbon, nitrogen, oxygen, these are capable of multiple bonds and allow you to branch out into a larger structure. Hydrogens are our fillers, and we'll use that to backfill the empty spots at the end. So starting with the atoms, we'll place the two carbon atoms in the center and then backfill or surround with hydrogens. In this case, I have 6 hydrogen atoms. Assuming I'll have a bond between the two carbons, I can place 3 hydrogens around each carbon atom, giving me C2H6, allowing me to check off atoms. I placed a single bond between the atoms so I know where they're connected, but later I'll show you how to find double and triple bonds. The next step is to make sure that every atom has a complete octet. I prefer to fill the octet, then adjust for electrons, not the other way around, and once you see this in action, you'll understand why. Hydrogen, if it has one bond, has a complete octet because it's an exception to the octet rule, so we don't even bother wasting time counting it. Each carbon atom having 4 bonds around it, that's 4 times 2 or 8 electrons, complete octet, we're good to go. Next thing we want to do is count our electrons. Do yourself a favor and count in 2. Whether it's a bond or a lone pair, it's always in 2s and it'll be so much faster. 2, 4, 6, 8, 10, 12, 14. I have 14 electrons. Let's see how many we need. 2 carbon atoms, each with 4 valence, should have 4 times 2, which is 8. 6 hydrogen atoms, each with 1 valence, should be 6. 6 and 8 gives me a total of 14. We have 14, so we can check off electrons. And last but not least, we have formal charge. In the last video, I showed you how to use my trick of should minus has to find the formal charge in a matter of seconds. I also told you that hydrogen atom, set it and forget it, don't bother with it. Carbon should have 4 valence electrons. Surrounding carbon, I have 4, no formal charge. Same thing for the other carbon, should have 4, surrounded by 4, 4 minus 4 is 0, our formal charges are good to go, our molecule is correct. Now let's see how we use this checklist to find double and triple bonds in the molecule by solving for the structure of C2H4. We start out the same way with our atoms, placing our least electronegative atoms other than hydrogen in the center. If we have 4 hydrogen atoms on a 2-carbon molecule, we'll give each carbon 2 hydrogen atoms. All our atoms are present. Next we go for the octet. Hydrogen is set it and forget it. Carbon has 1, 2, 3, 4, 5, 6, so we give it a lone pair. And the other carbon has 1, 2, 3, 4, 5, 6, so we also give it a lone pair. Octet is correct. Now that everything has a complete octet, we want to make sure that the number of electrons are correct, and if it's not, adjust it without depleting the octet. Carbon has 4 valence electrons times 2, gives me 8 electrons. Hydrogen has 4 times 1, which is 4. 8 and 4 gives me 12. If I count the electrons on the molecule, I have 2, 4, 6, 8, 10, 12, 14. I have 14 electrons, but I only want to have 12 electrons. If I take away 2 of the electrons from one of the carbon atoms, I depleted the octet, and that's no good. So here's what we're going to do instead. We have to somehow replace both sets of lone pairs with something that will not cut into either octet, but at the same time reduce the number by 2, as follows. Here it's easy, but in a larger molecule, find 2 neighboring atoms that each have 1 lone pair and put a bond between them. The bond cancels out the 2 electrons on the carbon on the left, cancels out the 2 electrons on the carbon on the right, but at the same time, we just replaced 4 electrons with a bond that has 2 electrons. Every carbon still has a complete octet, but my total number of electrons went down. Let's see. 2, 4, 6, 8, 10, 12. I should have 12. I have 12. We're good to go. Last but not least, we want our formal charge. Remember the trick, should minus has. Carbon on the left should have 4. Directly attached, we have 1, 2, 3, 4. 4 minus 4 is 0. Carbon on the right, same thing. Should have 4. Directly attached, 1, 2, 3, 4. 4 minus 4 equals 0. Now let's try this for a polyatomic ion. We'll use nitrile or Cn-. We'll start with the atoms. In this case, it's only 2 atoms. Carbon is less electronegative than nitrogen. Put them together with a bond between them. Atoms are in place. We'll give each one a complete octet by adding 3 pairs of electrons. Octet is complete. Now let's see how many electrons we really need. Carbon should have 4. Nitrogen should have 5. A negative implies an extra electron because that's the charge of an electron, for a total of 4 plus 5 plus 1, or 10. If we count the electrons we have, 2, 4, 6, 8, 10, 12, 14. We have 4 too many electrons. The way to reduce the number without sacrificing the octet is the trick of finding 2 neighboring atoms, each with a lone pair, and replacing the 4 electrons with a bond between them. So we'll take the top electrons from carbon and nitrogen and put a pi bond. We just reduced the count by 2. So we'll do the same thing again for the bottom pair of electrons, giving us a triple bond. At this point it's a little messy, so we'll rewrite it. Carbon triple bound to nitrogen. We have a lone pair on carbon and a lone pair on nitrogen. Verify that the octets are still there, because if you check off an item on your checklist, you can't undo that component. If we count our electrons, we have 2, 4, 6, 8, 10. We want to have 10, so we're good to go. And finally, we'll look at the formal charge. Carbon should have 4 valence electrons. Directly attached to carbon, we have 1, 2, 3, 4, 5. 4 minus 5 is negative 1, and that's where we have the negative charge on this molecule, but we're not done until we prove the nitrogen. Nitrogen should have 5. Directly attached, we have 1, 2, 3, 4, 5. 5 minus 5 is equal to 0, and that means the only atom that has an actual formal charge is carbon. The formal charge has to equal to the charge on your ion that you're given. If cyanide is given with a negative and our formal charge equals negative 1, we're good to go and our molecule is correct. We'll end with an exciting example, drawing out the phosphate ion, or PO4 3-. Starting with the atoms, we have phosphorus, which is the least electronegative, and 4 oxygen atoms, so we'll surround the phosphorus. Atoms are good. Next we'll go for our octet, starting with our single bonds, and then we'll fill in the atoms here. Every atom has a complete octet, so we'll check that off. Next we want to see how many electrons we have. Phosphorus is under nitrogen on the periodic table and has 5 valence electrons. Oxygen has 6 times 4 gives me 24, and a charge of negative 3 gives me an additional 3 electrons, for a total of 32. I'm going to show you a quick way to count this molecule without counting every single pair of electrons. Notice that we have perfect symmetry, such that phosphorus is bound to 4 groups that each have 1 bond, 3 lone pairs. So if we count 1, we can multiply it by 4. We have 2 in the bond, and then 4, 6, 8 on the lone pairs. We have 4 of these oxygens, each with 8 electrons. 8 times 4 is 32. Our electrons are correct, but this doesn't mean our structure is done. Let's take a look at the formal charge. Whatever we find for one oxygen will be the same for the others, because remember, they have the same number of bonds and electrons. Oxygen should have 6. Directly attached to the oxygen atom, we have 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is negative 1. That means every oxygen has a charge of minus 1. Phosphorus should have 5, but directly attached we have 4. 5 minus 4 is positive 1. If we add up the formal charges, it should equal to the charge on the ion that we were given. We have negative 1 times 4, which gives us negative 4, plus the positive 1 on phosphorus giving us negative 3. Everything checks out, and it looks like we're good to go, but we're still not done. You see, phosphorus is an exception to the octet rule, where it can have up to 12 electrons or 6 bonds. Whenever your molecule appears done, but you have a separation of charge, meaning a positive is next to the negative, one of the negative atoms will use its electrons to move the bond over and form a double bond. So even though it doesn't look like it right away, phosphate does have one pi bond between oxygen and phosphorus. We'll show that oxygen is having a double bond. Since it lost a lone pair, it now only has 2 sets of lone pair electrons, and the other 3 oxygens still have their 3 lone pairs and negative charge. So we still have -1, -1, and -1, but let's see what happened to the formal charge of the 2 atoms that changed. The oxygen used to have a -1, but now directly attached we have 1, 2, 3, 4, 5, 6, 6 minus 6 is 0, and phosphorus, which used to be +1, now has 1, 2, 3, 4, 5 attached, and 5 minus 5 is 0. So the formal charge disappeared on the phosphorus and the oxygen, but the other 3 oxygens still keep their charge, and so we have 3 times -1, which is -3, and we're still correct. So we know this is correct, but what if instead of the oxygen on the right, I chose to use the oxygen on the top or the oxygen on the left to form the pi bond between O and P? And the answer to that is what I'll cover in my next video, where I talk about resonance structures and the ability to move the pi bond around in your molecule. You can catch that video along with this entire series on my website at layitforsci.com/Orgo Basics.
Are you struggling with organic chemistry? Are you looking for resources and information to guide you through the course and help you succeed? If so, then I have a deal for you. A free copy of my ebook, 10 Secrets to Acing Organic Chemistry. Use the link below or visit orgosecrets.com to grab your free copy. After downloading your free copy of my ebook, you'll begin receiving my exclusive email updates with cheat sheets, reaction guides, study tips, and so much more. You'll also be the first to know when I have a new video or live review coming up. If you enjoyed this video, please click the thumbs up and share it with your organic chemistry friends and classmates. I will be uploading many videos over the course of the semester, so if you haven't subscribed to my channel yet, do so right now to be sure that you don't miss out.